Okay, now you will see my screen. Perfect. We will start with my part, the first part, and you should open this notebook. When you open it, you will find something similar, word SAMS disambiguation and embedding visualization. So if you want to copy it on your drive, it's very, very simple. You go to File, okay, and save a copy in Drive. And if you are logged in your Google account, you will find this notebook in your Drive. So if you have any problem, just type it on the chat. And I'm not looking the chat at the moment, but Matteo, tell me if there are some comments and stop me in case. Okay.
Okay, there is someone that can't see the desktop share.
Okay. Okay. Let's try again. I stop sharing. Now I start again to share it. Do you see my screen?
Yes, I see.
Okay. Andrea, do you see my screen?
Yes.
Okay, other people see the screen.
Perfect.
Okay, if there is a problem, I post the link to the YouTube live so that
then Matteo,
see the screen from there.
Stop me as soon as there is some problem, because as you can imagine, I'm now starting my presentation and it's difficult for me to simultaneously look at the chat. So
yes,
okay.
yes.
So guys,
if someone can switch from here to YouTube, so we can free some space.
Okay.
Otherwise, other people are locked out, and I'll put the link in the chat.
Perfect. So tell me if I can start.
Oh yes, you can start.
Okay, now you can see my screen. Perfect. Okay, yes. Guys. We just show you, me and Andrea, we will share with you our folder containing our notebooks, so you can copy them on your folder, on your drive without any problems. In 10 days, me and Andrea, we will better organize them and build a repo, and we will correct some typos, and if you have any suggestion, we will add them to the notebooks. So for the moment, we kindly ask you not to share them on the web or on social network at the moment. We prefer to review them and let's say in 10 days, publish them somewhere. So you can keep them for yourself, but please, at the moment, not share them on social network. So as soon as you open the notebook, there is a link to some slides. Okay, you see it? I open. This is some slides about my presentation. And okay, you can see me, you can see Andrea. And as I told you, we are colleagues. And this event is promoted by Machine Learning Milan with the help of the Italian Association for Machine Learning. If you click here, you can find the link. So you see, then after the presentation, you have a lot of link to connect with and to if you are curious about them. And okay, just a presentation about myself. Who am I? My name is Cristiano, and I'm let's say I'm a physicist. I took my degree in theoretical particle physics in Padova University. My thesis was about some formal aspects of string theory, that is a quantum gravity theory. Afterward, I took my PhD in SISSA, PhD in statistical physics at SISSA, working on entanglement entropy, a quantum information quantity relevant in many fields of physics. from many body physics to quantum computing and also to holography. After my PhD, I switched to artificial intelligence thanks to a master program. I will briefly talk about it later. Now it has been 3 years that I'm into machine learning, in particular deep learning and natural language processing. So somehow I close my path between the language of nature and the human language. And if you are curious about science communication, I recently gave a TEDx talk about, let's say, artificial intelligence and human creativity. So when you have time, you can watch it. Here you can find the link, just typing to the image. Currently, I'm working in Arman, which is a Samsung company. I'm, as I told, in the same team of Andrea, the next speaker. In addition, I spend a lot of time and efforts in education and science, technology, communication. Today is about, as a meetup, so is related to education and science communication. And I'm also collaborating with Aindo, which is a newborn innovative startup, is a spin-off startup from CISA, and is specialized in advanced machine learning solution for several sectors, especially biomedicine. So you can have a look on their website. You can find here the link. If you don't know anything about CISA is, I suggest you to have a look after the workshop to the website of CISA. Is a research center and a PhD international school where where you see pure research in physics, mathematics, and neuroscience is pursued. It's in Trieste, which is now awesome city. And CISA, together with ICTP, if you are interested in artificial intelligence and high performance computing, CISA and ICTP held a really hands-on master. I attended it 3 years ago during my PhD, and now I'm lecturing a deep learning class together with Alessio Sweeney in this master. This master takes more than 1 year full time to be completed, and so it's perfect for student and PhD, for master student or PhD students. And the applications are just now opened. If you don't have so much time and you are interested mainly in deep learning, I'm part of another master in Experis Academy, which is in Chilometro Rosso, close to Bergamo, together with other guys from Deep Learning Italia. You can find the link here of every stuff, you see, link. So I suggest you to watch them later. And okay, lecture of this master are not full-time, but just during the weekend. So, okay, let's start. This is the presentation. The outline of today's workshop will be a first use case. This will be my part. It's about word sense disambiguation and embedding visualization with the Italian Roberta, which is the pre-trained Italian pre-trained transformer model. But I will explain you later. And in the second part, Andrea will talk you about text summarization using text rank and Bert. Okay, this is not a typo. It's not Bert, but it's Bert. Okay. So let's switch to our notebook. Here you can find, okay, the slide. Here you can find all my contacts. For any question or doubts, you can find here all my contacts. And okay, I mostly post about artificial intelligence on LinkedIn and Twitter, but I'm also an Instagram addicted, and so you can find there also my Instagram. So let's start. What is Bert? Okay, we have no time to enter into mathematical detail, but you see, you can find here a lot of link. Bert is a transformer-based architecture. More precisely, is a stack of transformers, encoder layer that consists of multiple heads. Let's say fully connected neural networks augmented with the self-attention mechanism. The core of everything, in my opinion, is this self-attention mechanism. That is a non-local operator, which means that at any layer, a token, you see, here we have a sentence. Each token is transformed in a vector of 768 dimension. And so at any layer, a token can attend to all other tokens, regardless of their distance. Self-attention thus produces the so-called contextual word embedding, as successive layers gradually aggregate contextual information into embedding of the input word. So I repeat, we are not entering into much detail. We are using Bert as a black box for this workshop. But the important stuff is that the input of Bert is based on a sequence of tokens. The output is a sequence of vectors, one for each input token. We will often refer to these vectors context embedding. Why context embedding? Because have a look on these sentences. Wait a second, you first, I will be the second one. One of the great progress for this kind of models like Bert is contextual embedding. So Bert is able to distinguish the meaning of this second with respect to this second. You can easily understand that they have different meanings. And so Bert is able to realize it. The vector, the embedding which that represent the first second will be different for the second one, okay? So the conventional workflow for Bert consists of two stages, a pre-training and a fine-tuning for downstream application. In this notebook, we will deal with fine-tuning. In fine-tuning, one or more layers are typically added on the top of the pre-trained Bert. So what will we do? I will explain in this slide. So we want to solve a problem. Sorry, okay. We want to solve a problem. Just 1 second, that I have some issue with this window. Okay. We want to solve the following problem. You see, let's have a look in Italian first. Okay. For my part, I will work with an Italian dataset. Okay. In the second part, Andrea is going to work with English language, but in my part, we will work with the Italian one. So you see, we have a couple of sentences here. The first one is dimmi se ci sei stasera. In this sentence, sei is a verb. In the second sentence, in totale dovremmo essere in 6 stasera. 6 is a number. But you see, for a computer, in principle, 6 is the same word. How can a computer be able to distinguish the meaning? This was a issue, a problem for several years in computational linguistics. At the same way, in English, we can choose the word second. Give me just 1 second. Second is a fraction of time. But in this other sentence, I was the second one. He was the first one. Second refers to a position. So to understand the meaning, we must take into account context. This is the take-home message. So let's have a look. Before Bert and Elmo, so let's say till 2016, they were very popular non-contextual embedding, like word2vec and glove, in which each sentence, each token, it is represented with a vector, but say verb, and say number share the same vector, and as well as secondo. Secondo as a second, and as a second of time, and secondo as I arrived second at the match, they were sharing the same vector. So this is a non-contextual embedding. On the opposite, we have contextual embedding, in which this word split somehow their vectors according to their meaning. And some examples are Elmore or Bert-like algorithm. And so these are called contextual word embedding, word vectors that are sensitive to the context in which they appear. So this is the same image I showed you before about a Bert-like model. We have a sentence. Each token is transformed in a vector. Here we have some black box that we call Bert-like model, and the output will be new contextual embeddings in which each word, the context embedding depends on the meaning of the word. So, perfect. Now, we will start our hands-on. So, and okay, I switch on my notebook. Okay, a couple of disclaimer. This notebook is a bit advanced. The aim is not to let you understand all the details. We do not have time. The aim is to just let you aware of these powerful tools and have a taste of them. For any additional curiosity or question, feel free to ask us. We will not be mathematically precise. I know that among you there are a lot of physicists, mathematicians, theoretical physicists as me, but I will not be mathematically precise at the moment, especially about the geometry of Bert embeddings. They have been recently discovered and many studies are ongoing. So nobody actually knows how it works. I suggest you some interesting papers. You can find the link here. We will use some tools. First of all, PyTorch as a deep learning framework. Then we will take advantage a lot of Hugging Face Transformer libraries as an NLP toolkit library. Moreover, we will use the two most common Italian pre-trained Roberta, thanks to Giulio Ravasio and Leonardo Di Perna that generate Gilberto. And we will also use Umberto that was pre-trained by Simone Francia, Loreto Parisi, and Paolo Magnani from Music Match. I don't know if any of you is here attending this notebook, probably Simone, that I recently knew, but okay, here you can find all the links. Okay, we can start. We can, first of all, install the transformed library. Then we can import our tools, okay? And now we are going to check our GPU settings. And so we are going to check that we are on a GPU mode, just to let you know we will not train anything, but and here is just some lines that are used to check that everything is fine with the GPU, and as well with the memory. You see, I have a lot of memory on my GPU on Colab because I decided last month to pay Colab to have Colab Pro, and so probably you have a less memory here, but does not matter. So we prepare for you some data, okay? Because you see, we want to solve this problem about disambiguation of the word say. Okay, in Italian, in Italiano, say has at least two meanings. Can be a verb or can be a number. And we want to distinguish them. So we can download this data that I prepared for you. You can find them here. We will check the size of them. I don't know if you are aware of it, but if on Colab you put the exclamation mark, you can use the bash part of Colab. And let's check our sentences. Our data set is very, very simple. We have some sentences. Let's have a look at the first one. Dove sei stato e cosa hai fatto? And we label it with 1. We have a second sentence in which we have sei ancora suo collega in azienda, vedo. And we label it with 1 because sei is a verb. But the next one, i due ebbero 6 figli e 11 nipoti. We label it with 0. Okay, because here say is a number. So very, very simple data set, guys. I tried to stay simple just for the lack of comprehension, okay, to be more clear as possible. So this is a very easy problem. It's not something revolutionary, but okay, the aim of the lecture is to let you understand. So as you can see, our dataset is made of 2 types of sentences, and they are labeled, okay? They are labeled sentences. Sentences with say, verb, and number. This dataset was built scraping different sources from the web. And okay, we then choose a fixed length to filter shorter sentences. Okay, here I build a class that is called the dataset loader, blah, 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 in which I can choose the Bert type to use. You see, I can use Gilberto, I can use Umberto, and this function, this class, sorry, will prepare somehow our dataset before giving it to Bert. So before giving any inputs to a Bert-like model, it's important to prepare the sentence the way Bert like to ingest it. In more technical words, we must tokenize properly our input. A tokenizer is in charge of preparing the inputs for a model. We will use pre-trained tokenizer, but be aware that you can train your own tokenizer. So a tokenizer is something that prepares the string, the sentence string, to be ingested to a Bert-like algorithm. And here, with a flag, we can choose to use or Gilberto tokenizer or Umberto tokenizer, or if you wish, you can try several stuff. We can use also multilingual Bert, and also the distill one. But okay, we will not touch them. We will use the first 2 in this notebook. So, okay, this function is a bit complicated, but I somehow unrolled the function for you here. What is going to do this function? Very simple. We have a sentence, ciao come stai, cosa fai stasera? Probably I was thinking about a girl when I typed this sentence, but you see, let's have a look what is the process. So first of all, the sentence enters into a tokenizer, okay, and it will convert each token with a number corresponding to a dictionary of the Bert vocabulary. But it's very simple to understand. Okay, there is a flag here. Look here, add special token true. So during this process, this tokenizer will add to the sentence, have a look here, will add two special tokens that are, in the case of Roberta, called S and this other symbol. Okay, if you are more confident with Bert, Bert calls the first token here CLS, like this guy. Okay, sorry. For Bert is CLS, okay, but it's just a matter of name. And you see, we have a sentence, ciao come stai, cosa fai stasera? This sentence is converted in some digits, and then is some special token are added, and then we are going to pad this sentence. We decide a max length, because you see, this kind of algorithm like Bert, but not only Bert, they work with a fixed length, a fixed vector length, and so we decide to choose a length. And if the sentence is shorter, we will add some zeros. And then we will have also an attention mask that it's a technical vector to let Bert aware if where there are some real tokens corresponding to words, and instead tokens corresponding to padding. And so you can look at it carefully later, but it's clear. So this is the tokenizer. And we will, we will then use this data loader that combines a data set and a sample and provides an iterable over the given data set. So in very simple words, we add the path of our data set, and the data loader will provide us, let's say, a useful way to collect data for PyTorch. So train loader and validation loader. Guys, these are very technical stuff. I'm a scientist and I'm not a software engineer, and so I don't want to spend time understanding how PyTorch or TensorFlow, if you are using TensorFlow, are elaborating data structure. I don't care about them. For me, this is just technical stuff. So let's run this cell. I choose some parameters. I choose a max length of 50. At the moment, we are going to use Gilberto as our pre-trained notebook, pre-trained model, a batch size of 8, and okay, during the training, let's fix to 5 the epochs. So model definition and training. Now we are able to define our model. You see, I choose to use, let's say, a class to define my model. And it's very simple. We have different models. As I told you, we have Gilberto, Umberto, and so on. And okay, here we have the model, auto model, Bert model. In this case, before, we were using the tokenizer, auto tokenizer, okay? If you have some confidence with Hugging Face, you will recognize some pipeline, common pipeline for Hugging Face. So here we have our pre-trained model. We choose Gilberto for the moment. And then we will add, let's say, another layer. I will show you here. You see, this is the pre-trained model that already knows Italian, but we want to fine-tune it. You see, fine-tune it to a specific task, that is distinguish classifying sentences with say verb or say number. And so this is fine-tuning. We add another layer, this green one, that somehow will let this new model stronger for this specific task with respect to the base one, to the starting point. And so what we are going to do is very simple. We will take our data set that is labeled, and we will supervise the fine-tuning our model, and it will generate some embeddings, different embeddings with say. So this model here, with the green part is nothing else than this part here. I'm just adding, you see, here we have the Bert layer, the pre-trained, that is this one, okay? And to this one, we add the green one, and the green one is this one. We will just add a classification layer, okay? Linear layer in PyTorch language is fully connected, dense layer. And you see, we have a binary classification. So here I put 1, and here is the dimension of the output, is the dimension of the contextual embedding. So the output of Bert will have this kind of dimension, very huge dimension. And this is just a dense layer, okay? This is the green part, the green part that you can see here. Somehow I attached to the pre-trained Bert classification layer. Okay. Okay, I used this kind of class way to define the model just because if you have much more fantasy than me, you can add here other layers, okay? You can add a convolutional layer if you wish, LSTM, whatever. And so instead of using the, let's say, API from Hugging Face, here you can model as you prefer your layers. And so this is our model. Then here we have some function, utility function to get the accuracy during the training and the evaluation. Here we have some other function that will help us to evaluate our model. And you see, when you are working in PyTorch, differently from TensorFlow, when you start evaluating your model, you must put this part, so net evaluation, and you evaluate this model. Another specific part of PyTorch is this torch no grad, and so you are telling to the algorithm not to optimize, not to update the weights of the model, because you know, in evaluation we are not training the model. And so this part together with this part is safe to you. Okay, it's safe because you just evaluate in the right way your model. Okay, so evaluation function. And okay, here is the training function. You see, at each epoch, we will do an evaluation. So the epoch after evaluation, our net model is on eval mode. You see, eval mode. So we need to switch to train mode after each epoch. Because in train mode, for instance, we enable the model to learn and to its weights to be updated. Moreover, we enable the model to activate the dropout. You see, here we have some dropout layer that during evaluation is switched off. Instead, during training, we want dropout active. And so, remind, it's very important in PyTorch to pay attention to this kind of, it seems irrelevant, but is not at all, okay? So here is a common training. During training at each epoch, you give some training data, okay? You split them in the sequence, the attention mask and the labels. I remind you that we are doing supervised fine-tuning, so we have some labels here. This is the net. You put this kind of sentences, so sei andato a casa stasera with corresponding attention mask, we give it to the model and it will output some logics that will be a number between 0 and 1. Okay, have a look here. The output of our net is a number between 0 and 1. Okay, because you see here there is 1. And okay, this is the output, and what we usually do in machine learning, you see, this is an advanced somehow workshop. I'm not explaining how deep learning or machine learning works. I, let's say, understood them. And so, as usual in machine learning, you put the output of the net and you match it with the labels using a criterion that is a loss function in PyTorch. Then I will show you what we are choosing. And so this is our loss function, and we then apply back propagation, and we optimize our weights. Okay, this is the common pattern pipeline in machine learning. At every 100 step, we compute accuracy, blah, blah, blah. And if accuracy, and after each epoch, you see, we are going outside this for loop. After each epoch, we are going to evaluate on a validation set. So here we are training on training set, and here we are evaluating on a validation set. And then here we save the model. Okay, we do not have time to enter into all the details, but you have everything explained here. This afternoon, tomorrow, and whenever you want, you can somehow understand any details, and if something is not clear, just write me. Okay, and if you find also some typo, just write me. And so let's run this cell, and here we can start our training. You see, we fix some seed. This is our net with flag Gilberto. We put it on CUDA, on GPU. We use as a loss function the binary cross entropy with logits loss. And we use Adam optimizer with a very, very low learning rate, because when you are fine-tuning a model, it's a good practice to use a very, very low learning rate. Because you are doing a fine-tuning, you are not training from scratch as the guys from Gilberto or Umberto did. We are not training from scratch on Italian, we are just fine-tuning. So we don't want to mess up what the guys from Gilberto and Umberto did for us. So very low learning rate. So we can start the training, but you see, this kind of training will take something like 20 minutes, or we do not have time. So let's just see the first output, and then we will stop it. In the meantime, if you I don't know, this afternoon you want to train your own model, then you want to save it, this is the way to save it on your Google Drive. Okay, perfect. So you see, iteration, loss, and accuracy obviously is very low because we are just starting. But now I will interrupt this training because we do not have time to finish it, but it's working. Okay, now obviously I already trained for you two models. One is a fine-tuned model with pre-trained Gilberto, as we were doing before. The other is with his friend that is called Umberto. Okay, so we have here, I just download them from my Google Drive. We have Gilberto fine-tuned, you can see it here, and we also have his close friend, his brother maybe, Umberto. And so we put them inside our folder models. Okay, But now, since before we used Gilberto, and Umberto was a bit sad about it, now we will use Umberto, okay? And so let's choose Bert type Umberto. Now, okay, we have already trained our model, and it is here. I trained it for you yesterday. And so what we are doing now is inference and then embedding visualization. And so for inference, we will run again our models. Here we will find our before model, the one I showed you before, that now it's called fine-tuned net, but it's really the same as before, with the classification layer. You see here, dropout classification is the same as before. But I also add another model that I simply called net, which is just the pre-trained Roberta model, okay, without a classification. We will use it later, but I will run it now. And the idea is to compare what? Compare the pre-trained model with the fine-tuned one, okay? That's why I'm running, I wrote both of them, okay? So here are our model. We will load them. We will load, you see, net, and we put it on evaluation because we are going to do inference. And so we want not to mess up the weights. And so it's put on evaluation mode. Is downloading Umberto pre-trained model. And we also load our fine-tuned model, the one we somehow trained before, but I trained for you yesterday. And I loading into this fine-tuned model, I'm loading the weights. So you see, we have our two models. Here we load also the respectively the Gilberto and Umberto tokenizer. And you see, below we define a couple of useful functions, okay? The first one, model inference, given a sentence, we will predict its class. The second one, you can read it here, the second one will extract embeddings. If the arg specified token is chow, it will extract the embedding of token chow. If the specific token is the special token, it will extract the classification special token. Okay, so model inference and embedding extractor. It seems a mess for you, but don't worry, because I will run them and we will see them step by step. You see, model inference. If you give a sentence to our fine-tuned model, arrivato fino a qua, sei ancora attento? Let's have a look. Ah, okay, model fine-tuned. Sorry, I missed to run probably a part. Give me just 1 second. Okay, this cell must be also here. Okay. Okay, max length. We need also, I didn't run a cell probably before. Max len equal okay. Why is not defined max length? Sorry, but okay, because here it's sorry. Okay, I discover a typo. Perfect. Okay, that's fine. You see, arrivato fino a qua, sei ancora attento. This is the sentence. First of all, we'll translate as we saw before in the corresponding vocabulary item. We will pad it, and you see this model inference will give us just a number between 0 and 1. In this case, it's telling us that this say is a verb because 0.78, it's much closer, it's greater than 0.50, and so it's a verb. And so this is just model inference. It will output the probability. If to be precise, below 0.5 is much closer to 0, and so is a number. Above 0.5 is much closer to 1, and so the probability is that is a verb. And let's see the embedding extractor. The embedding extractor is very similar to model inference, but you see, we can give a specific token to extract. I want the specific token of say I'm telling to the embedding extractor. The sentence is this one. I want to extract the embedding of say. And okay, have a look on the shape is 768. If I remove shape, you can see this vector, this huge vector is the embedding of the word say according to the context of this sentence. Okay, that's clear. So then you can look the details of this function, but this is the output. Okay, now we can test our model on sentences he has never seen before. We just select 200 sentences just to be fast, and we have our model. We choose Umberto as a pre-trained and then fine-tune model, and we can compute some prediction on these test sentences. So we have these sentences. Tu sei andata con l'altra ragazza a mangiare. In this case, say is a verb. Amico mio, non sei mai salito più in alto. In this case, is one. Okay, is a verb as well. In this case, are number. And now we are checking if Umberto fine-tuned, it's able to infer correctly on the test set. And so we just computing using, you see, model inference, the function we just saw above, this one, that gives us some probability. So we compute it, and now we check the performances, and they are very, very good. Look at the confusion matrix. There's just a couple of errors, and he really classified them perfectly. If you want to have a better view, okay. Now that we know that the guy, the model has correctly classified our test set, we are going to visualize the embeddings of the test set. And so what we are going to do now, I'm computing, extracting for each sentence of the data set, of the test set, I'm extracting the Bert of say, sorry, the embedding of say from our fine-tuned model. And have a look here, I'm also extracting say from the base model, the one without fine-tuning, because I want to understand if Roberta, if Bert, in this case Umberto, it's able, without fine-tuning, to distinguish already the meaning of say. And so we are extracting now the embedding from the same sentences. Okay, the sentences were this one, 200 sentences. Okay, and after that, you see, we need to use or TSNE or UMAP to project 768 dimension down to 2 dimension, okay, in order to plot them. So we use UMAP and TSNE. What I'm doing is very close to one of the paper I link you above, in which they are studying the geometry of Bert. And what they are doing is exactly what I'm doing now. So I'm not as much as clever to invent it by myself, unfortunately, but I'm a good reader. So I read carefully that paper, and I'm just replying it. I now collect, we can skip this cell because I'm now just collect everything in a data frame just to plot them. So nothing scientific interesting, just collecting on a data frame what the coordinates of the UMAP and the TSNE that I compute in order to project this very huge dimension of the Bert embedding. So I decide now to plot both UMAP and TSNE results. This is the plot, and have a look. Let's have a look here. For instance, you see, on the left, okay, on the left, we have the results of Umberto without fine-tuning. You see, the base one. On the right, we have the result of Umberto fine-tuned. And so, have a look how it's able to cluster the sentences. So here we have sentences in which sei is a number. Sono 6 anni, 6 anni fuori, and so on. Here we have sentences in which sei is a verb. This is the UMAP presentation. Unluckily, the green dots here are covered by the legend, but they are here. You see, you can have a look and look at them. You can also look at the misclassified one. Okay, and this is the TSNE. If you prefer TSNE to UMAP, you can have a look here. But the important point is that Umberto, also before fine-tuning, it's already able to distinguish the meaning of sei. Here is a number and here is a verb. You see, after fine-tuning, probably the cluster are better defined. It's more, obviously, it's more precise, but also before fine-tuning, there are very good results. But now, and in 3 minutes, I finished. You see, this is for me amazing because before Bert, this kind of results were just one vector. Instead, here, Bert or Roberta, or more in general, Bert-like models are able to distinguish really the meaning, not only between numbers and verb, but among numbers, you can find different subtle differences between the meaning of a say. One say could be a number, another say could be a time. Let's meet at 6 p.m., for instance, okay? So it's able to distinguish it. But my last point is the following. Suppose to have some data that are not labeled as the one we used before. So we do not know if now I'm choosing another word that is secondo. Secondo in Italian has a lot of meaning. Could be the time, secondi di tempo, può essere i secondi, siamo arrivati secondi alla gara, ma può essere anche secondo me la politica sta sbagliando o sta facendo giusto. Oppure può essere il secondo come il piatto, ho mangiato un primo e un secondo. So, secondo has a lot of meaning. And I'm not able to prepare a data set classifying, labeling them correctly. So I can give some sentences to Bert, okay, to, let's say, Umberto, and let him predict this kind of different cluster. And then if I want to distinguish them, I can use a k-means algorithm or a clustering algorithm more in general to color different clusters. And so let's have a look here. I just download some sentences in which secondo is present. They are, I took them from Oscar, a very popular data set in NLP that it's called Oscar. You see, these are the sentences. Here there is, you see, secondo il formato, secondo me. And so we are going to give these sentences to Bert, in particular to Umberto, and we will let him classify, extract the embedding. Okay, so it will take just a few seconds. In the meantime, then we will apply, as above, UMAP and TSNE, okay, just to collect these embeddings into a data frame. And then we will plot, we will apply a k-means algorithm. I choose 6 different meanings for my word secondo, and color the sentences. Okay, now it's running, but to save some time, there is already this plot, and look at it. Let's have a look here, that how Umberto is already able to distinguish 1, 2, 3, 4, 5, 6 cluster. And you can appreciate that, for instance, here we will find secondo as a time, just a second, for instance. Here you will find secondo me, secondo te. So I invite you to have a look, but the important point is that you see these different clusters are different meanings in Italian for the word secondo. And so somehow I finished, and the take-home message is that Bert-like model have a very sophisticated geometry. We do not know a lot of geometry of this kind of model yet, but what we know is that they are able to distinguish different meanings of similar words. And this is very important for a lot of application. Think about sentiment analysis. For instance, in English, long is a word that could be positive, for instance, a long vacation, but at the same time could be negative. A long queue, I'm stuck in Milan into a long queue. This is negative. Instead, going abroad for a long vacation is a positive meaning. And so Bert is able to distinguish them. And okay, I hope that, okay, I did a lot of stuff, sorry. And but the important stuff, I'm sorry that if I did not dive into many details, but we had limited time to really understand and have some confidence with transformers and Bert from theory to practice. At least one need of lecture is needed. The important point here, and I hope you appreciate it, is that you have a complete notebook for you, full of details and references, and you can have a look at it more carefully. And feel free to contact me or Andrea if you have any question. You can find here the link here or in the first slide, the link. And so thank you so much.
Thank you, Cristiano. And I think there are a few questions.
Okay, just one point. Okay, it's fine, but I don't want to steal a lot of time to Andrea, but you can type the question on the chat and I will try to answer. I don't know, Matteo, let me know about timing, if we are on track or not. Let me know.
Yes, a few.
Okay.
You can answer just a few questions
Yeah.
Okay, so the first question was about why you select output 0 from the Bert layer.
Output 0, ok, aspetta. Where exactly? I don't output 0?
Yeah, because I'm reading that from the chat.
Okay, I just have a look to the chat. I don't know where is the chat, unfortunately. Okay, chat. Sorry, but...
Okay, from the Bert layer to the linear layer.
Okay. From the Bert layer. Okay, where? Here. Okay, here. Okay.
Yes.
Yeah. Because now the task was a classification task between sentences with in which say was a verb and sentences with say is a number. And if you have a look at the documentation of Hugging Face, you see, I was prepared for this question because a lot of people asked me before. So have a look here on the output of Bert model. Okay, if you have a look here, you will recognize that on returns the output, and what I'm selecting is the pooler output. That is, you see, the first token of the sequence is the classification token. And so I put 0 because of that array. I want to select the first token, the classification token, for the fine-tuning of my data set. So you see, that's the reason why I put this 0. The answer is the documentation of Hugging Face. You must see here. Okay, if otherwise, without 0, I'm going to collect all the embeddings of an array containing all the embeddings of all tokens. Instead, for this particular problem of classification, I was interested on the classification token that is one of the special token that the guy from Bert, the Google guys, invented because it's more useful in classification tasks, as we were doing. I don't know if I answered your question, but I hope, yes.
Yes, and so there was another question, if we tell in any way to the model to have attention on say, on the word say, but probably the answer is no.
No. It pay attention to all the tokens in the sentence. What I'm doing, I'm just extracting the output of say because I'm interested. Okay, during classification, yes, during this classification task is a specific downstream task that I choose just for the lecture. But in this case, obviously, is somehow paying a little, I'm somehow biasing the model on the word say, because it's present in all the sentences, and moreover, the sentence is labeled with referring to the meaning of say. So when I'm classifying it, yes. But when I'm using Bert based without fine tuning, as I told you, we used Umberto, in that case is not biased and is working well anyway. Okay, I use this classification task just to give you a pipeline for a classification problem, but for this specific disambiguation problem, as I show you, Umberto already is able to distinguish without fine-tuning. Okay, this is just a workshop. The intention was to give you as much material as possible.
Okay, I think we can let Andrea talk.
Yes.
If you can answer the questions in the chat, so that
yeah. Now I will have a look in the chat. Sorry, but I didn't have time. And I remind you, for any question of my part or whatever, also advice for machine learning, science, blah blah blah, whatever. Here are all my contacts. You can add me, write me, and so thank you so much. Bye bye. Bye, Andrea.
Thank you, Andrea. Sorry, Cristiano.
Vai, ho tolto lo schermo e adesso mi silenzio. Sono anche un po' stanco di parlare. Ciao ciao.
All right. So good morning, everyone, and welcome to the second part of this workshop. So in this section, we'll talk about text summarization. So can you hear me? Can you see me? Everything is okay, I hope, at least. So if you haven't already done it, you can, from the shared folder on Drive, you can take there is the part 2 slides. You don't need them, but if you want, you can download them, as well as the notebook here. So you can just deploy it in your collab if you want to follow with your own notebook this part of the workshop. So let me see here. Okay, so let's start with some slides. First, I will close this one. Okay. Perfect. So 30 seconds just to introduce myself. As Cristiano said already, we work together with many other people. We built NLP models for Harman and Samsung. I started as a theoretical astrophysicist, and then I worked as a Python developer and as data scientist for a couple of companies. And now we do NLP stuff. And this is my contact in case you want to write me or to connect. So let's jump into text summarization. First of all, what is text summarization? So as you can imagine, automatic text summarization is the task of producing a summary without human aid, with a computer, therefore. So what's a summary? There is no clear definition of a summary, but loosely speaking, we can say that it's a text derived from the original text, from another text, that is much shorter than the original text, is concise, is fluent, is grammatically correct, all this stuff, but also it has to preserve the content and the meaning of the original text, right? So there are two main types of summarization. This is not only for summarization, but for instance, also for question answering. So there is extractive summarization, meaning that the summary is composed by words and sentences coming from the original text. So like a marker underline, basically. And then there is abstractive summarization, which is where the summary is composed by new words, new sentences not present in the original text, like a pen writing, basically. So text summarization is really, really hard. And there are two reasons for that. The first one is that producing a summary with a computer is not easy at all. So we as humans, when we summarize some text, we read it, we understand it, we contract it, we do all complicated stuff. And from a computer point of view, this is very difficult. This is really is a non-trivial task. Also, given a text, we can have multiple good summaries, right? So there is no one single best summary as well. The other point, the other problem is that we also have no clear robust method to evaluate the summaries we generate with our computers. So usually we use Rouge scores, but these Rouge scores have a lot of problems, so they don't tell the whole truth about the quality of the generated summary. And it's not rare to use human evaluation, which is still the best way to evaluate generated summary. So it's for some papers for some authors, they pay or ask people actually to evaluate their summary. So there are many techniques that we can use to summarize a text, many techniques. Here we will focus on two. One is simple, and it's more like an information retrieval kind of technique, which is called text rank. that is based on graph and is used for extractive summarization. So we are going to extract the most important sentences from a text we want to summarize. And then the second part is a bit more complex. We will use Bert, which is a sequence-to-sequence transformer. And so we are talking about supervised learning. And this can be used for both extractive and or abstractive summarization. So for the first part, for text rank, we are going to implement the method by ourselves using as few libraries as possible. We are basically going to use only NumPy. So we are going to be very, very verbose in our code, very inefficient as well. So the idea here is just to write it down to understand it, right? To look at line by line so we can understand what text rank does. And for Bert, we are going to take the opposite path because this is a very complex and big model. So we are just going to use a very simple function to generate some summaries. So more on this later. So let's talk about text rank. If we want to talk about text rank, first we need to talk about page rank. Page rank was a method invented by the Google creator, I think still used by Google in some form, along with the Bert here you've seen before, and that allows us to rank web pages. So imagine you work at Google, you have a user searching for something, you have a set of web pages, you can display that to him, and you want to sort these pages in an order fashion, right? You want to put the most important one as first and the least important one as last. So you can use PageRank, the scores of each page, which is the page rank of each web page, to sort the list and present the list to the user. So the idea behind PageRank is to organize the web pages in a graph. So each node is a web page. So here we have 4 web pages, and each web page is connected by a link. These are the edges, called edges. So for example, here you have web page A, which has an outgoing link to web page C. That's the idea. So we can compute the page rank of each of these web pages, and this page rank, for instance, the page rank of A is the measure of the relative importance of A with respect to the whole set, to the whole graph. So in order to compute the page rank, we need to solve this equation. We are going to solve this iteratively. So this is composed by 2 terms. On the left-hand side, you see basically a matrix multiplication. So this page rank is a vector, and the dimension of the vector is the number of nodes of the graph, so the number of web pages. And here we have a matrix multiplication. This M matrix is called the transition matrix, which is basically represent the probability of transitioning from one page to another using the links that we discussed before. So here there is the transition matrix for this example, for the graph we've seen before. So the columns, and this is a symmetric matrix, so the number of columns is the same of the number of rows, and the columns are the outgoing links, the rows are the incoming links. So for example, if we sit on A, so the first column, we see that there is only one link to page C. So it's all zeros, but the third row, which has 1. Same for B, right? We sit on B, so we are in the second column. We have 2 links, one to C and one to D. So it's all 0, but the third row, which is incoming link to C, and the fourth row, which is incoming links to D. So here, basically, we sit on B, we have just 1 click. What is the probability of going to C is 0.5, because there are 2 links in B, and the probability of going to D is 0.5 as well. So we have a uniform probability of going from B to C or D. Then it's the job of the page rank to weight these probabilities in order to get to the most trusted source. So for instance, if C has a higher page rank, which means that it's is a more trusted source, then it means that we will weight more this probability here on the third row, and vice versa for D. You can also see here that there is a D factor. This is called damping factor, which is basically the confidence that we put in the modeling of this graph using this incoming outgoing link situation. And you can see that on the right-hand side, there is also 1 minus t, which basically means that we also add this term, which is the modeling of randomly shifting between nodes. So as an example, you can see here that A doesn't have any incoming links, but still we have this contribution because we're considering that we can randomly move between nodes even without these incoming links, outgoing links. So for example, let's say that we are on D, and we just, instead of clicking on links, we just write the address of the web page A in the address bar, and we press enter. In this way, we just went to page A. So that's why there is also this right term. So why are we talking about page rank? This is because text rank is the equivalent of page rank, but for text. So in this case, we have a text we want to summarize. We can split this text into sentences. And now the nodes are not anymore the web pages, but they are the sentences composing the text we want to summarize. And the edges, so the connection between the nodes, is a measure of the similarity between these sentences. So each node is connected to every other node, unless, for example, here between B and D, there is no similarity. So the idea is to do the same of page rank. We're going to compute text rank for these sentences. So one text rank score for each of these nodes, for each of the sentence. Then we're going to order them starting from the sentence that has the highest text rank to the one with the lowest one. And then we select the top K sentences based on their text rank score. So that's the idea. So we're going to solve the same equation as page rank, which is this one on the right. We just simply change the matrix, right? So before we had this transition matrix M, now we have this similarity, sentence similarity matrix S. So we just need a way to find S, to compute S, and then we are good to go. We are good to compute the text rank. So we need two ingredients to compute the sentence similarity matrix. First of all, we need to pick a similarity measure between sentences. There are many options. For example, we can pick the cosine similarity, which measures the cosine of the angle between two vectors. This is the formula here on the left. On the right, you see the cosine similarity for words. So these vectors are the word embeddings. And we are going to do the same, but instead of words, with sentences. So the vectors in our case would be the sentence embedding. So the translation of a sentence from text to number to a vector. So now that we have picked the similarity measure, we just need to find a way to convert our sentences, our text, into vectors, into sentence embeddings. There are many ways to do that. For example, we can use term frequency, inverse document frequency. So the TF IDF is basically the multiplication between two terms. The first one is the term frequency. So given a word in a sentence, we are going to count how many times this word appear within the sentence, and when we normalize it, we divide it by the length of the sentence, by the total number of words of the sentence. On the other hand, we have the IDF, the inverse document frequency, which is the log of the inverse of how many sentences contain that word divided by the total number of sentences. So the idea behind TF-IDF is basically that if a word appears a lot in a sentence, then it would have a high term frequency, right? So it gives us information. But if this word also appears in the other sentences, if it appears a lot also in the rest of the text, then the IDF will be low. So we counteract, we decrease the TF-IDF by having a high TF but a low IDF. And the idea is because if it appears a lot also in the rest of the text, it probably doesn't bring too much information. Imagine, for instance, the article the, right? It appears a lot in a sentence, so it has a high TF, but it doesn't really bring too much information. So we have a low IDF to counteract the high TF. So at the end of the day, we compute the TF-IDF for each word in each sentence, and we're going to use them to get the sentence embeddings. So what we're going to do basically is, first of all, we compute a vocabulary, which is a unique set of words of our text that we want to summarize. So for instance, here there is an example on the right. You have just two sentences, high word and a low word. So the vocabulary, the unique set of words that compose the whole text would be high and low and word. So this vocabulary, the words inside the vocabulary, they are the dimensions, they are the axis of the embedding space. So in this case, our embedding space will be three-dimensional, and the axis are the words of the vocabulary. And then the sentence embeddings are these vectors, where the coordinate of these vectors are not other than the TF, RDF scores of these words, of the words within the sentence in each dimension. So for instance, for the sentence high word, we would have that in the axis high, in the dimension high, we will have that the coordinate would be the TF-IDF score of high in this sentence. On the axis word will be the TF-IDF score of word in this sentence. And also, of course, there is no hello, so the third dimension, the coordinate on hello would be 0. So this is what we're going to do in the first part. So let's jump into the notebook here. So if you want to run it as well, remember to activate the GPU. You can do it here by clicking on runtime, change runtime type, and select the GPU. Okay. So let's connect the notebook. So first of all, we're just going to import some libraries. So here we're just installing a transformers library we'll use later on. Here we will import some stuff, some libraries as well. So let's look at our first function. Perhaps I can zoom in a bit. Our first function computes the text frank score. So remember that this is the equation we want to solve. We're going to solve that iteratively, as we said. So it takes as input a matrix M, which in our case is the sentence similarity matrix that we're going to compute later. You can see that there is the damping factor. There's also a tolerance one here just to stop the iteration. So we're going to iterate and stop the iteration when the newly computed text frank, when the difference between the newly computed text frank and the one at the previous iteration is below this tolerance. So here we initialize a bunch of stuff. So here we get just the number of nodes, which are the number of sentences, right? So the number of rows and columns of the similarity matrix. Here we initialize just the first value of text frank for the iteration, also the difference for stopping the iteration. So as you can see here, it's a very simple function. Just the core of it is this simple equation, right? And we're going to iterate on that. And then here we just update diff to stop the iteration. So let's run this function, and this function will compute the text frank given the sentence similarity matrix. So now we need to define how to compute the sentence similarity matrix. So the first way is to, the first thing to do is just to define this function, which computes the cosine similarity between two vectors. Very simple. And we're going to use that in the next function, which computes the sentence, the similarity matrix. So remember that our for this function, our goal is to define a matrix where the position ij, and given that this symmetric is also the position ji, there is the cosine similarity between sentence I, between sentence I and sentence j. So this function will take as input this features array, which are the sentence embeddings. First of all, we create a 0 matrix with the same number of rows and columns, which is the number of sentences, which is the number of rows of the sentence embeddings. And here we fill the values. So we loop over the elements, and at position ij, we put the cosine similarity of sentence I, of the sentence embedding I, and the sentence embedding j. Given that this is symmetric, the similarity matrix at ji is equal to ij. And then we normalize it column-wise. So let's run this as well. Okay, so now we have the function to get the text rank given the similarity matrix. We have the function to compute the similarity matrix given the sentence embeddings. We just need a way to compute a function to compute the sentence embeddings. So this is what this function does. It takes text, so the entire text we want to summarize, and it produces sentence embeddings, so one vector for each sentence in the text. So first of all, here we just clean it a bit, and here we get the we compute the vocabulary. So we remove some punctuation, etc. We assume that the words inside the text are separated by a white space. So we're going to split on the white space, and then we'd apply a set here to just remove the duplicates. So the vocabulary will be the unique set of words or of the entirety of the text we want to summarize. So we take then the text and we split it to get a list of sentences of the text. So we assume that the sentences are separated by a full stop here, and we get a list of sentences of the text we want to encode, that we want to summarize. So here we loop over the sentences, and for each sentence we get a list of words of the sentence that compose the sentence. So once again, we remove the punctuation, we assume that the words are separated by a white space, and we get a list of words. So now, while we are looping over the sentence, first of all, we can compute the turn frequency. Remember that the turn frequency is the number of times the word appears in that sentence divided by the length of the sentence. So we're going to do that. We loop over the words and the vocabulary, and we count how many times the word appears in this word list of the sentence divided by the length of the sentence. Since we are here, we are also computing the denominator of the IDF. Remember that the IDF is the log of the total number of sentences divided by how many sentences contain that particular word. So if we find that this word is inside the sentence, we are just adding a +1 to the denominator of the IDF. So now we finished looping over the sentences. We have just computed the denominator of the IDF, so we can compute the IDF, right? So we can do it here. For each word, we will get the IDF of the word is the log of the length of the total number of sentences divided by the denominator of the counter we just computed above. And finally, we have the TF, we have the IDF. We can then compute the TF-IDF by just simply multiplying them together. So here there is a bunch of print stuff, and you can see here at the end, we just convert the TF-IDF as NumPy array, and we return it. So let's run it and let's see an example of this function, just to have an idea. So imagine we have this text, which you can see is composed by 3 sentences. And using the function we have just defined, we're going to get the sentence embeddings for these 3 sample sentences. So if we run this cell, you will get this output. So you will get the denominator, first of all, the denominator of the IDF. So you can see here, the columns here, this is our vocabulary. These are the dimension of our embedding space, the axis of our embedding space. So the denominator of the F, once again, is the number of sentences that contain that word. For example, for sentence, you see it's 3 because it's in all 3 of these sentences, but 1 is only in the 3rd one, and so on and so forth. So then we take the log of the total number of sentences, which is 3, and we divide it by this denominator IDF, and we get this IDF, the inverse document frequency. Also here we print the turn frequency. The turn frequency depends on the sentence. So here we will have 3 rows, each for 1 for each sentence. So the first one is the first sentence, second sentence, and so on and so forth. So for example, you see that in the word sentence, in the first sentence, actually, well, let's see with the word is, it's easier. The word is in the first sentence has a turn frequency of 0.2 because it appears 1. and the length of the sentence is 5, so it's just 1 over 5, 1 divided 5. So at the end of the day, we can take each of these rows, multiply them by the IDF, and we get the TF IDF. So here, each row is the sentence embedding of the corresponding sentence. So we're going to use these vectors. Right? This is just an example. We're going to use these sentence embeddings to compute the text rank. So imagine now that we have everything, right? We have the function that computes the text rank, the function that computes the sentence similarity matrix, the function that computes the sentence embeddings. So here is just a simple function to select the top k sentences after we computed the text rank. So it takes as input the text, and the text rank it computes. It gets a sentence list from the original text. It sorts the text rank starting from the highest text rank to the lowest, and it uses that to get the top k sentences from sentence list. In this case, k equal 3. So it will return the top 3 sentences based on their text rank score. So we define this, and finally we can put everything together. This is just a simple function that calls all the other functions. So we just need to call this one. So this function just giving the text to summarize. It first produces the sentence embeddings. Then it passes these sentence embeddings to the get similarity matrix to get S. This S goes as input to the compute text rank to compute the text rank. And finally, given the text rank here, we can extract the top k sentences. So this is just a wrapper, basically. And here is just a very simple function to, print the summary. So let's run it. We are going to use this a lot. So let's try now to summarize a text. So what I did, I went to the Guardian website, and I took a random news article from that website. Guess what? Unfortunately, it's about the COVID virus. So sorry about that. So let's define the article, and then let's use our text rank to extract the top k, the summary, which in our case is the top 3 sentences, extracted sentences from the original text. And this is exactly what we do here. So if we run this, we have a lot of output. If we go at the beginning of the cell, you can see that once again, we print the denominator of the IDF. This will be our vocabulary. Then we have the IDF, the turn frequency. These are the TF IDF. So these are our sentence embeddings. And you can see there are 12 rows. So we are dealing with 12 sentences. This is the similarity matrix. And here you have the iterations that for the text rank. So it stops right here at the 10th iteration. So the first value is the text rank of the first sentence, the second of the second sentence. So for instance, you can see that the highest text rank is for the 7th sentence. So our summary, you already know from here that our summary will start with the 7th sentence coming from the original text. And the original text is here. It's just splitted, sentence by sentence, so you can understand the extraction a bit more. So I give you a minute just to read it, to summarize it in your head, so then we can talk about the summary that we just extracted. Okay, so as you can see from the summary here, as we said before, we extracted the 7th sentence as the highest text rank one, which is this one. Then we extracted the following one, the 8th, which is this one here, and also the second to last here. So as I said, I mean, it's difficult to evaluate the generated summary, but you know, personally, I'm satisfied by it. For instance, if I had to perform extractive summarization by myself, I wouldn't have included, say, the last sentence here. I don't think it's very important, as well, for instance, as this sentence here, slabs of beef and pork, and I think it doesn't bring too much information, so I'm glad that our text rank has not selected them. So of course, this is just a simple approach. There are many other more sophisticated way to do text rank. So this concludes our part of the text rank. If you want to dig in a little more deeply, I've come up with some exercise you can do. They are in order of difficulty and also time requested. So feel free to do 1, 2, or even none, of course. So let's then switch to the Bart part. Before we head back to the questions, perhaps, and also to the slides, I would like to ask you to run, if you're running, of course, the notebook with me, the 2 following cells, because we're going to load very big models, so it will take a while. So while we talk about other stuff, it will download. So we run this first cell, which is just the device we want to use, in this case, the GPU, so it must be CUDA. And here we start to load a bunch of stuff. Okay, so now we can head back to the slides. I don't know if there are any questions concerning text rank. Let me know, because I don't really see the chat anymore. Not sure why. Okay, chat. Let's see. Okay. So the first question is, for what do you use text rank at work? Well, personally, my work is for just single document summarization. Of course, you can use it with a bunch of, for a bunch of applications. Actually, text rank, for instance, you can also use it for keyword extraction, not only for summarization. One of the version of text rank, which is called lex rank, is part, it was invented being part of a very big summarization algorithm that was tackling multi-document summarization. So you have multiple documents with multiple inputs, text as well. So, I mean, text rank is very easy to do, it's very fast, so you can use it for a lot of applications, also in conjunction with other methods. So, I mean, it's a really broad answer, I would say. The other question is, would it be a good idea to run lemmatization? Yes, also probably, well, I'm not sure about for summarization, but also one can think also about stop words as well. This is because we have used TF-IDF sentence embeddings. So they are really basic embeddings. They're basically bag of words on steroids. So they base their computation on the kind of overlapping between words in different sentences, right? Because we use the sentence embeddings for TF-IDF plus the cosine similarity, which means that, in instance, we are not considering the synonyms between sentences, you know, and this kind of stuff. So we are trying to match the exact word. If we want to look at 2 sentences and check if they're similar, we are trying to look at the exact match for each word in one sentence and in another. So yes, lemmatization, of course, will be a good idea. Otherwise, in general, something that is not that strict and is not that limited in confronting sentences, trying to match the exact words, that will be, of course, more useful. What if you use sentence embeddings from Bert? for representing sentences. Do you think it's a good idea? Yes, this is one of the exercises I wrote down. Well, for Bert is not that direct, I would say, to get out sentence embeddings. But of course, yes, it would be, I think, using sentence embeddings from Bert would result in a better extraction. But it's also true that at this point, getting the sentence embedding from Bert and use them on TextRank, I mean, the first part, the getting the sentence embedding from Bert, will be much slower, will be the most time-consuming part with respect to TextRank. So at the end of the day, do you really want this trade-off, right? Do you really want this very big, complicated model to extract sentence embeddings and use then this sentence embedding in a very simple model? I don't know. I've never tried. I don't know if someone has tried this. But of course, yes, you can do it. I think it's a good idea.
Andrea, if
yes.
I can ask just I read the last question about sentence embedding, and so if you wish, you can use my notebook and do not extract the say token, but the special token, and you will have the sentence somehow the embedding of the classification token. Or if you put as a flag of specific token known, my function automatically will extract you the average of the embeddings, and somehow it's thought to be a sentence embedding, and then you can use it with the notebook of Andrea and try whatever you want. So I was just want to add this point that from my notebook you can change that flag and put known or a specific token, sorry, special token to extract them. So.
Okay, so let's go ahead because we are running out of time. We are really late. So let's switch to Bart now. Let's go to the slides. So what is Bart? Bart stands for bidirectional and autoregressive transformers. It's a model proposed by a group from Facebook AI last October, so few months ago in this paper here. So basically Bart is a sequence-to-sequence, therefore encoder-decoder transformer model that is able to replicate the results of encoder-only, decoder-only transformers, while also, of course, we're talking about NLU tasks, so natural language understanding tasks or discriminative tasks, while also setting very good results, sometimes state-of-the-art, in generative tasks, so in natural language generation tasks. So basically, Bart is part of this new wave of transformer models that use an encoder-decoder architecture instead of encoder-only, decoder-only architecture. So before you use Bert, which is an encoder-only architecture. So here I show you on the left basically an incomplete list of encoder/decoder-only transformer models, while on the right you have the encoder-decoder models. So you can see here from the dates that 2018, 2019, and even now, these were the years of encoder-only/decoder-only transformers, while lately, starting from 2019 till now, and probably till the end of the year or more, more and more encoder-decoder models were presented. And also don't forget that the original transformer, which is this one, was an encoder-decoder architecture. And this is because it was thought for machine translation, which is a generative task. So in general, say, as an example, you used Bert before. Cristiano showed you how to use Bert to do sentence classification. So once you have one input, once you're doing the so-called NLU task, natural language understanding task, so you have one input and you work on that. You're trying to understand what's inside. You're trying to characterize what's inside the input. So for instance, if the word say was a verb or a number. But in our case, for summarization, and also for machine translation as well, we are doing generative tasks because we have an input, so the text we want to summarize, and we want an output which is different from the input. So we need to use an encoder-decoder architecture. So here we skip it. So the architecture of the transformers is this one. So there is a lot of stuff. We don't care about, you know, this left part, and also forget about this right part. Let's just focus on this one. On this one, you have on the left an encoder layer. So this is the encoder. Of course, you have multiple layers stacked on top of each other, and this is exactly what you did with Cristiano. You use these stacked encoder layers. You took the output here. You put a classification head on top, and you classified 0 or 1. In our case, we also are considering the right part. This is the coder layer, and the output, we're going to use the output of the encoder, and we're going to feed them to the decoder. So as you can see here, we have two kinds of inputs. The one is the input of the encoder, which is our text, our input text. And also we have an input of the decoder, which is the output of the decoder shifted right. More on this later. So there are a lot of complicated operations, you know, position right, feed forward, normalization, residuals connection, this kind of stuff. But at the core of the transformers, there is the attention, right? And you discussed that before. The attention, loosely speaking, measures the importance of each word with respect to every other word. So here we have three types of attention, you see here. So one from the encoder and two for the decoder. So the one of the encoder is the one that you used before. It takes the input and it processes the input using this bidirectional self-attention. Also, we have another attention here for the decoder, which is kind of similar. We'll discuss this in a second. And also we have a third attention, a second attention in the decoder side, which is where the magic happens. So here is where we connect the encoder with the decoder. So the input with our output. This is also called cross attention on or encoder-decoder attention. So as you can see, basically that this attention, they actually perform exactly the same operation. We just change the input of this attention. So let's try to understand this encoder-decoder architecture, so this BART architecture, discussing Bert and GPT approach for pre-training. So you have seen this before, right? Bert is composed by bidirectional, also called fully visible encoder layers. So this is one encoder layer. We've seen this in the past slides. So Bert uses an autoencoding approach. Formally is not really an autoencoding approach, but whatever. So what we're doing for Bert is that we say we want to predict using this architecture here, so using this multi-head bidirectional attention, we want to predict a word, say that here. What we're doing is to consider bidirectionality, so we're looking both at the left and at the right of the word we want to predict. We process all of this stuff, all of this context, as we said before, to predict the word that. So what we are doing is to model this conditional probability distribution. So we want to model the probability of getting X at position T, given everything that it was on the left, everything that was on the right, and also the same token just masked, and of course the weights of the net. So this is called masked language modeling or closed task. On the right, we have GPT. GPT uses a different approach. It uses autoregressive decoder layers. So it uses an autoregressive approach. So remember that here, this one was the decoder layer. So first of all, there is no encoder here because there is only decoder. So actually, we don't have this cross attention, this encoder-decoder layer we discussed before. This is not present for GPT. So if you look at the two layers, they actually are the same, basically. The only difference is this masked multi-head attention. And the difference is because here Bert is bidirectional, while GPT is autoregressive. So let's say that we have the same sentence of Bert, and we want to predict the same token. With GPT, we use a mask self-attention, so we shift right the input sentence, and we mask everything that is on the right of the token we want to predict. So given I want to eat, we predict that. So we are modeling this conditional probability distribution here, which is language modeling. So we want to model the probability of X at the position T, given only everything that is on the left, and given also the weights. So, but for instance, you can, for Bert, this bidirectionality was also was a choice, right? If you look at the appendix of the Bert paper, you will see that there is a comparison between a bidirectional Bert and a left to right Bert, which uses this kind of approach here as for GPT. So it's just a matter of choice. As you can see, the difference between the two is not that dramatic. So why are we talking about Bert and GPT? Because if we sum up these two approaches, then we kind of get Bart. So remember, Bert uses bidirectional encoder. So we have an input, we mask some words, and we want to recover them using this bidirectionality, looking at both left and right. For GPT, we are going to, what we do is to use autoregressive decoder. So we start with a single token here, this special token called beginning of sentence token, which is kind of, we say to GPT, okay, let's start decoding. So given S, we predict A. Then we take this prediction A and we put it as input here. So given as A, predict B, and so on and so forth. For instance, for D, given as A, B, C, predict D. So we look at the left and we do that iteratively. So BART is more or less the composition of these two approaches. It uses a denoising autoencoding approach. So it's composed by bidirectional encoder layers, and the output of these layers goes into the autoregressive decoder. So what we do, first of all, we take some input for the pre-training, of course. We take some input and we inject some noise. And this noise is sentence shuffling. So you can see, for example, here that B is in the third position while it should be in the second. And also we do text infilling, meaning that we sample some span of text and we remove this text, we replace that with one masked token. So given this input with a lot of noise, we process that with this bidirectional encoder, we pass the output of the encoder to the decoder, and we ask the decoder to autoregressively recover the input, the total input, without the noise. So this is what the pre-training is for BART. So for us, we're going to use BART large, which is composed by 12 encoder layers and 12 decoder layers. So now that we have this pre-trained BART, which in principle should be able to kind of understand the language, we can fine-tune it on our specific task. Of course, there are many ways to fine-tune it. For example, you can fine-tune it for machine translation. We are talking about summarization, so we use, BART fine-tune on summarization. So the process of fine-tuning is the following one. We give the encoder side, as encoder side input, we have the text we want to summarize. The encoder then processes that, and the output of the encoder is fed to each layer of the decoder, and the input of the decoder is just the output of the decoder shifted right. Okay, so of course we are talking about supervised learning. So that means that we have an input text and also the reference summary, the gold summary. Okay, so we put them as input for fine-tuning BART, so that BART, using the relation between the input text and the reference summary, can understand kind of the rules of summarization. So in our case, we are not going to pre-train or fine-tune BART. We will use already fine-tuned models. And this is because we don't have time and we don't have resources to do that. Just to give you an idea, one of the version of BART was pre-trained on 256 V100 GPUs. So if you consider that a V100 GPU costs around 5 to 10,000 euros, you will need kind of 2 million euros worth of GPU just for pre-training, let alone the electricity bill. And the suggested number of GPUs for fine-tuning is 8 8v100, so you will just need 80,000 euros or so. So as you can imagine, we don't have the resources and the time to fine-tune or pre-train Bart. Fortunately, Facebook they fine-tuned Bart already for us, and they released the models. So we're going to use these models and use them to do some inference to generate some summaries. So we're going to use two different models because Bart was fine-tuned on two different summarization datasets. One is called CNN or CNN-VM, and the other is called XSum. So remember, we are talking about supervised learning. So the model learns from the data. And that means that the data we fine-tune on set the degree of extraction and abstraction of the model. So for example, CNN is composed by news articles from CNN and Daily Mail, and the summaries are typically related, so the labels are typically related to the source text. So this model is kind of in between extractive and abstractive, perhaps is a little bit more extractive. While for XSum, the articles come from the BBC, and they're usually way more abstractive and much shorter. So this model, the model fine-tuned on XSum, would be way more abstractive than the CNN one. So what we're going to do is to perform some inference. So what that means that we are going to, basically we are not going to iterate to perform this operation because this is done internally inside the transformer library, but it's still good to understand what happens inside. So remember, we are just doing inference, so there is no reference summaries, there is no labels, it's just the text we want to summarize. We put that as input, and as before, we ask the model, so the model at the first time step, we will start with this input, beginning of sentence input, and we will output this. Then it will take this and put it here on as the input of the decoder, and so on and so forth, until it generates the end of sentence token. So what we are doing here is basically we are modeling this conditional probability here. So take the probability of the next word we are generating for the summary, given the previous words of the summary we have already generated, given the input text we want to summarize, and given also the weights, the fine-tuned weights of Bart. So, for example, we can look at time step 3 and ask ourselves, given that I just predicted DCs, so I'm asking the model to predict the third word, given DCs, given the initial text. So how do we pick this word here? Because remember, we are modeling this probability distribution, and this probability distribution is over the whole vocabulary. So what we have is that we have 50,000 words, each one with its own probability, and we need to pick one. How can we do that? So the first and the most simple idea is using the so-called greedy search. So why not take the word that has the highest probability? So here I give you an example. Given disease, we predict the next word. So here we just show 3 words, but they are 50,000. And we take the one with the highest probability. Then we do the same, given this is the, we predict the next words. And we take, once again, the one with the highest probability, etc., etc. So basically, out of all the possible paths of generation, we have selected this one, the one that at each time step maximizes the probability of the word, which is good, but, and this is greedy search, so it's good, it's easy to do, it's fast, but it also has the tendency of missing high probability words hidden behind one or more low probability words. And for this reason, we use bin search, which is exactly the same as before, because in fact, greedy search is a special case of bin search, but we follow not anymore one single path, but we follow a number of paths that we decide. So in our case, it will be 2. So we generate text for all these bins, for all these paths. We keep track of the sequence. So in this case, we are not anymore maximizing the probability of the word that is generated, but we are maximizing the probability of the sequence, of the path, which is the multiplication of the words. So at the end of the day, if you look at this simple example, you see that we have two beams. The first one, the green one, is the same as for greedy search. But for beam search, we select the beam that has the highest probability in terms of sequence, so in terms of multiplication of words, of the probability of the words. So actually, in this case, we would select the second one because the model is more confident on this sequence. And you see here the difference in probability here. So while for greedy search, we have taken this path here, it's true that at the third time step, so while we were generating this, the model was more confident for the word with respect to the model A. But if you look after this selection, the model was less confident, the probabilities of the next word were lower. So therefore, even if A has a lower probability with respect to D, then actually the model is more confident for this generation here. So we usually use beam search instead of greedy search to generate this text. And by the way, we as humans, we actually don't perform beam search. So this is time step of generation, right? And you can see that the beam search, the blue one, tries to maximize the probability. Sometimes it doesn't, as it should. While we as humans, we are way more irregular. We don't maximize probabilities. And this is explained beautifully in this paper I suggest, which also introduced the nucleus sampling. So at the end of the day, beam search is okay if we are doing summarization translation. If you are doing open-ended generation, then use top K, or even better, the top P sampling, which is introduced here. So let's go to Bert and start generating to the notebook and start generating some summary. So at the end, here we have just downloaded the two models, so the CNN and the XSum models. And here we define a very simple function to generate the summary. So we take the tokenizer, because we need to tokenize the input text, the model, so it could be the CNN one or the XSum one, and the input text we want to summarize. So first of all, we tokenize the text here. So in case you're interested, the Bert uses a byte level, byte pair encoding tokenizer like GPT-2. I think. So here is where the magic happens, right? Internally here, you have all these iterations, all the stuff we showed in the slides. So this method takes this input, so the tokenized text we want to summarize. We can set the maximum length of the summary, of the output summary, also the minimum length. We can also set the size of the n-gram that we don't want to repeat. So for instance, if we set this to 2, it will mean that bigram cannot be repeated. Like if our summary contains New York, it only contains New York once, for example. Here we have the number of beams for beam search. So it means that if it's 1, it's greedy search. And here is the number of sentences we want to return. So let's say we do a beam search with 10 beams. We can, for example, put here 5, and this will return the top 5 beams in terms of probability of the sequence, order, of course, by this probability. So this gives us this output. Here we just decode them, we convert them back to strings, and this will be our summary or our summaries. So very easy to do. So let's try it. First of all, let's try to generate a summary with greedy search using the CNN model on the Guardian article we have seen before. And we print it. So here, once again, you have the original text. And right here, there is the summary. So you can see that basically the Bert CNN has extracted some stuff, some parts of the text, of the original text. He kind of merged them together, he chopped them a little bit. So for example, here you see open air markets is actually open air settings, so we perform some abstraction, as well as in the following one, where locals buy fresh meat, etc. You see here that actually it comes from the first sentence, but there is no such a sentence. So that means that it's just copied the last part here, and he abstracted, putting something new at the beginning. So you can see here there's kind of a bit of abstraction, a bit of extraction. And also here, for example, you can see the last sentence of the summary comes from the second to last. So it was extracted, but you can see that continue to was chopped out. So this part was removed by the model. So now let's try with beam search. We will use a beam size of 10 and we will return just the top 5 beams, just for question of space. So first of all, as you can see that the this time with beam search, the summary is different with respect to greedy search. This is expected. Also, you can see that they start with the same sentence, and then they kind of diverge. They take different paths, but more or less they are kind of a slightly different version of one another, basically. So if we compare the summary we have found, of course, the first one will be our final summary because it's the one with the highest sequence probability. So if we compare the summary found with beam search, with greedy search, and also with our text rank, here, we can do it here. So you've seen that I think both, all 3 summaries are good. They can be acceptable. Interestingly, you see that the first sentence of the beam search is more or less the same as the third sentence of greedy search, which also is the third sentence of our text rank. So all these 3 models, they agree with each other that this sentence is one of the most important sentences from the original text. So now that we have seen how this BART CNN behaves, what we can do is to try to push a bit the limits, try to break it, try to find the limitations of BART CNN. Because remember, both BART CNN and Exam, they have been trained over news article. So what if we give them something with a different style in a different domain? Does it work? Does it work or does it break? Something like that. So in order to do that, I took the beginning of a short story by Borges, and let's see how BART CNN behaves, trying to summarize this story. So as you can see, the story is has a style that is completely different from the news articles. Also is a first-person story, so the main character is telling the story. So what you can read it is not really, something difficult. Actually, it's just a guy that tries to find this city, that's in search for this city of the immortals, basically. So the summary here is quite interesting, because what BART CNN did was to extract, even just for extraction here. So it was in difficult times, didn't know what to do. So it tried to leverage something that it was able to do. So, okay, let's go for extraction. And as you can see that from the summary here, the first part of the summary, this is just the first sentences here, the first 2 merged together, basically. And the second part of the summary is the extraction of this sentence here. You can also see that while the second part has this quote already, the first in the original text did not. So I actually performed a bit of abstraction because he put this first part between quotes. I think here what he did was to, usually in the news article, when you see a first person talking, is about, is an interview or a quote or something. So he kind of understood that here there was the main character speaking, it was a first person narrative. So he put quotes on the text because that's what he was told to do, right? He was told to do. So that's how the news articles work. So let's try to push the limit a bit further. Let's try to break it more. So here I took a very lyrics from a song, and very complicated, very difficult to summarize even for me. And let's see how BART CNN behaves on this very difficult text. So as you can see here, this is the original text. The text is very difficult, very short, pieces of sentences. The sentences are broke down. There are a lot of repetitions. Also here we see in new and lost is repeated a lot of times. It's basically a guy that is in angst and tries to, you know, dance to keep it light, to kind of fight his own inner demons or something like that. So let's see how BART-CNN behaves on this very difficult text. And once again, he relies on extraction. So it takes some sentences and it just puts a full stop after that. You see here, this one is this one. Sometimes he is able to understand that different lines are different, are the same sentence, like here, or all this law will be in vain, like here. But for instance, this one, he wasn't able to do it because he put a full stop. So this is a really difficult text in general. If I had to do extraction here, I would probably had taken this one as the most important sentence. As my world comes crashing down, I'm dancing. And here you can see that actually this was one of the extracted sentences. So I'm pretty satisfied by it. Of course, this is not a good summary, but at least it did something right. And also it did a bit of abstraction. You can see here that as my world comes crashing down, it puts a very poetic and artistic comma before I'm dancing. So I'm a bit moved by the choice of BART-CNN. So let's try now to do the same, but this time for BART-Exam. So we're going to summarize with this very abstractive model. And also we'll print the summary from BART-CNN just for comparison. So let's start with the Guardian article, talking about wet markets. So as you can see here, the summary, it's basically the model is already broken. The summary is completely nonsense. I mean, it's very well written, but there is no such information as the letters from this African journalist, this columnist, whatever. So he understood that we are talking about the coronavirus, about Wuhan, but this is completely wrong. It's just made up some stuff. Probably this kind of beginning was very frequent in the exam dataset. So he went for it, and of course this is complete garbage. So let's try to do it with another. I took a random web page, and let's see. This is called Bus Radar, and let's see how both exam and CNN performs on this text. So just to summarize it, this is basically the description of a product. I think it's a travel company, a bus company, or something like that, or so kind of. I think no, it's a website that allows you to find, bus companies to get the best prices, the best tickets, and something like that. So if we compare, this is interesting because if we compare, this is the summary by exam. This is the summary by CNN. You can see that they both start with the same sentence. And this sentence was extracted from the text here. The intercity bus enable you, blah, blah, blah. The difference, you can really see the difference here because BART-CNN is more extractive. So he just extracts the sentence, he puts full stop, and then he starts with something else. While exam is more abstractive. So instead of putting a full stop in there, it generates new words after that. And it actually generates a question mark as well. So, and if you look at the final part of the summary, this is more like something you can find in the advertisement. So it understood that we are talking about, a service or something like that. So he wants you to try, he wants to advertise this service. So I think for exam, in this case, the summary is really good and is also well written, I would say. Concerning BART-CNN, once again, more extractive, so it's kind of doesn't go for the A+, but still the summary is reasonable. So last two cells, then we're done. Let's compare exam and CNN on the short story. So this is the exam summary. this time, I mean, the summary from exam is very well written, but it didn't really get it. I mean, if you look at the summary here, and if you look at the original text, it's not really what happens. So the content, the information from the original text is not really preserved. It has a lot of problem. I mean, the Mauritanian traveler was not, you know, it is not told, the text, the story was not told by this Mauritanian traveler and so on. So it's not really correct. Nice style, but wrong. And we already seen that for the Bart CNN is more extractive. So last cell, let's see for the song, for the lyric song. For exam, once again, it's garbage. So once again, in our series of letter, as we saw for the article. So he understood that we are talking about music, but apart from that, it's all completely wrong. While for Bart CNN, of course, we have seen it relies more on extraction. So for him, it's easier to get it right. And also, he put this fabulous comma that is very artistic and poetic. So of course, it's the best summary. So this basically concludes our workshop. So as you can see, we have compared the XSUM and CNN models. And we have seen that they have very different behaviors, and this is because they were trained on very different data. And they're like two students, right, doing a test. They study more or less the same stuff, but when they have to answer a question and they don't know the answer, the XSUM student kind of goes for improvisation. He either goes for the A+ or for the F, while the CNN one is more conservative and tries to leverage what he knows. So perhaps he goes for a C or a B. So at the end of the day, this once again shows us the importance of the data we are training on. So as for the text rank, if you're interested, there are a couple of exercises here. They are very, very simple, very, very fast. You don't need GPUs, you don't need data, etc. It's just a continuation of what we have seen so far, you know, playing around with the generation, with the inference, and so on and so forth. So thank you for your attention. Then let me check if there are some questions. So here we are. Okay. So let's see. Part as a service, blah, blah. Okay, so are those Bart large models multilingual or English only? Most of them are only English. There is a multilingual Bart. I think they released just the pre-trained multilingual Bart and the fine-tuned one on the machine translation between English and Romanian. So, okay, so Claudio Bottari asks again, are there any Italian training Bart models? Unfortunately not, but the multilingual Bart has been trained on, I think, 25 languages, including Italian. So you can use that, but remember that, you know, fine-tuning or adapting Bart is really huge. So you need a lot of GPUs, you need a lot of resources. Probably the basic requirements would be something like a GPU with 16 gigabytes of RAM and a lot of gradient accumulations. So the other question is, what are differences among BART and T5? And what would you suggest for summarization? Thanks. Yes, so you can also use T5. T5 stands for text-to-text transformer, I think. It was a model from Google. You can use that as well for summarization, of course. I think the T5 was pre-trained and fine-tuned in a different way. I'm not an expert, but basically it uses exclusively text text objectives. So for instance, it didn't use 0, 1 for classification or something like that, but only text. T5 also comes, I think, in different sizes. And there is the huge one, which is 17 billion parameters. So in general, if you look at the size and at the performances of this model, what you will find is that Bert and ProfitNet, they are able to more or less give the same results in summarization with respect to, say, T5, Pegasus, and this kind of stuff, while being trained on less data. And T5, as we said, depending also on the one you pick, but if you have enough resources, you can go for T5 as well, for the large one. Personally, I prefer smaller models. So personally, for summarization, I would use Bert, but I must say that I haven't tried T5 for summarization, so I don't know which one performs best, to be honest. Question for the first part of the talk. So this is about a question about text rank. What is the distribution of ranks? Instead of taking the top case sentences, does the rank distribution show some clear separation? If so, do you think a simple cluster algorithm will be able to select the K, the number of most representative sentences? Yes, I think so. The point here is just that perhaps you need longer text, I would say. So for texts that are composed by a few sentences, perhaps this is not effective. But I would say that for longer sentences, you actually can use this clustering approach to select the K. This is fine. Also remember that there is no, even if you use a very sophisticated model to select the K for the top K, remember that there is no perfect summary, there is no best model, so there is no best K. There are also clustering, instead of using text rank, you can directly use clustering algorithms on the sentence embeddings. This is another solution. So let's see for other questions here. For multi-language models, isn't also the tokenizer a bottleneck for optimal performance? Well, yeah, in general, this is also for Bert, not necessarily for Bart, but usually for multi-language models, yes, you have bigger vocabularies. So of course, you will have some, I wouldn't say problem, but some degradation of the performance once you look for your token to be connected with the idea of the vocabulary. But anyway, we are talking about a factor of something like 3. So it's not a factor of 30 or 100 of vocabulary sizes between the multilingual and the monolingual model. So yes, there is a bit of that, but I wouldn't worry too much. Yeah, that's correct. Also, there is this new library from Tokenizer, which is much faster, and I think it will be included in the Transformers library as well in the near future. So I think I answered more or less, yeah, all the questions. Yeah, okay.
Thank you very much for the talk. Both of you, they were really, really interesting. And
Thank
so
you for following us.
I think we can end the meetup here. Also, thanks everyone for connecting.
All right, thanks a lot then. Have a nice Saturday.
Bye-bye.
Bye.
Bye.
Thank you so much.
Thank you.
Bye, thank you.